Right, quick video this time. Three-dimensional vectors. This kind of concludes the chapter. This is year 13 vectors from the pure maths. And I'm just going to look at a couple of applications in mechanics. So first of all, we're going to look at F equals ma, but where F and A are both vectors. M is obviously a scalar because it's mass. One quick example question. A particle of mass 2 kilograms is acting on by two forces. We've got P and Q. Oh, I should probably put those that they are newtons. They are in newtons. Calculate the acceleration and the magnitude of the acceleration of the particle. Okay, well, it's just a case of applying these into this this formula over here. So the resultant force is the sum of all the forces that are acting on it. So we've got 2 minus 1, 3, plus minus 1, 4, minus 1. And that's going to equal the mass, which is 2, we're told that's 2 kilograms, times the acceleration, which we don't know what it is yet. And if we sum those two vectors and then divide by 2, we'll get that the acceleration is 2 minus 1 divided by 2 is a half. Minus 1 plus 4 divided by 2 is 3 halves. And 3 minus 1 divided by 2 is 1. Okay, so that's the acceleration. We've done the first part of the question. Okay, calculate the acceleration. That's it. And that would be in meters per second squared because the mass is in kilograms and the forces are in newtons. So everything is SI. Okay. It also wants the magnitude of the acceleration. Okay, just refer you back to a couple of videos to find the magnitude of a vector. We're going to use Pythagoras. So the magnitude of this acceleration is going to be the square root of a half squared plus 3 halves squared plus 1 squared. Okay, and we'll just leave this as an exact number. So square root of 0.5 squared plus 1.5 squared plus 1 is root 14 on 2, so a half root 14. Okay. Approximately 1.87. Okay. So the magnitude of a vector is Pythagoras applied to that vector. And don't forget, three-dimensional Pythagoras, you just add in the third dimension into the square root. Okay. Second application is with either suvat or, in this case, we've got a variable acceleration, so with a bit of calculus. So an object is initially stationary, apologies, and accelerates at a rate of a, which we're told is 2t minus 5i plus 3t squared minus 10tj plus 3t squared minus 25k. What other time, other than t equals 0, is the object momentarily stationary? Okay, so for stationary, we require the velocity to equal 0. Okay, that's what it means to be stationary. To be momentarily stationary means it is only stationary for a tiny fraction of a second, which means if you move a tiny bit to the left in time or a tiny bit to the right in time, it is moving. So it is stationary for an infinitesimal amount of time. Okay, well, how do we get from acceleration to velocity? Well, we need to think about the rules to get from acceleration to velocity, and we integrate. Okay, if you're unsure whether you need to differentiate or integrate, just think about the units. Okay, this is ms to the minus 2, so that's some kind of length divided by a time squared. And if I times it by a time, which is what the t dt does, that leaves me with a length over a time, which is a velocity. Okay, so you can think about it using the dimensions. Now we're just going to integrate a vector. Okay, it might not feel quite normal to you, but it doesn't change anything. It just behaves. I is just a constant, j is just a constant, k is just a constant. So just all the normal rules of integration just apply. So we're going to integrate. I'm going to write this as a column vector. So 2t minus 5, 3t squared minus 10t, and 3t squared minus 25 dt. Okay. So we integrate that. That's going to be t squared minus 5t in the x direction. In the y direction, it's going to be t cubed minus 5t squared. and in the z direction it's t cubed minus 25t. And then we also have a constant of integration, but this time the constant of integration will be a vector. So C1, C2, C3. That is our constant of integration. Okay, well, how do we find the constant of integration? Well, we're told that it's initially stationary. Okay, that means that when t equals 0, v equals the 0 vector. That actually tells us that our arbitrary constant vector for our integral is actually the 0 vector. However, if this were a question and you ignored this vector altogether, you would lose a mark. You have to consider it and then show that it's 0. Okay, you can't just ignore it altogether and expect full credit. So this then says that the velocity is equal to t squared minus 5t in the I direction plus t cubed minus 5t squared in the j direction plus t cubed minus 25t, and that's in the k direction. All right, we want to find when the velocity is 0. Well, we know the velocity is 0 and t is 0 because that was one of the conditions. So we can actually divide by t, and we end up with t minus 5, t squared minus 5t, and t squared minus 25. We want that to equal the 0 vector. The top line says that t is 5. The next line down says t is 0 or t is 5. And the third line down, it says t is plus or minus 5. So the only one that's consistent with all of those is t is 5. And to be stationary, all of those components, the x component, the y component, and the z component must all be 0. So the only time that happens is when t is 5. Also when t is 0, but we didn't want that one. So I divided by t. So t is 5 is my solution to the problem. All right, thanks for watching. I'll see you again.